Okay, good afternoon, everyone. Um, so, welcome to this lecture 10. We'll conclude our discussion on the foundations required for optimization and move on to conditions for optimization with and without convexity. So, you'll see that some conditions are irrespective of convexity, some are incumbent on convexity. Um, so, yeah, so this is where we are. We're almost done with all these subgradient conditions. Just a very brief recap and then move on to convex optimization problems. And as I said, optimality conditions and then Lipschitz properties of functions. This is what we will do today. So I had left some homework problem for you guys, right? And the homework was really understanding the first order conditions for convexity, but characterized differently. It is, in this case, the rate of change of the gradient or subgradient, right? So far, we looked at convexity. So convexity, we had, when I say convexity and its variants, I mean strict and strong convexity. So we had several equivalent definitions, right? One was from first principles. If you take f of theta x plus 1 minus theta y, just evaluate a function at a convex combination of 2 points, that should be less than or equal to the convex combination of the function evaluations, right? Then we had a second definition, which was if you were to evaluate the function at y, then what would happen? This would be lower bounded by the function evaluated at x plus this linear term, but this linear term would amount to a linear approximation of the function at x using the gradient at x. Right, so this, what was the interpretation here? This interpretation was the fy here is greater than or equal to fx plus this gradient transpose y minus x. Now there is a third definition, and the third definition is based on the notion of monotonicity of gradients or subgradients, right? And what is that interpretation? Well, it's saying that this gradient, if a function is convex, how should the gradient be looking like? What would we expect? What would you expect the first derivative of the function? In the case of R, it would be increasing, right? The gradient keeps the derivative keeps increasing. So basically, monotone subgradient. I'm using the word sub here because I would like you guys to think on how much this holds for subgradients as against strictly full gradients. So this is basically saying what? If this is my definition of monotone, right? Strict monotone, strong monotone, blah blah blah. That's okay. What would I expect? As per this third definition, gradient at x minus gradient at y. Or if you want to call it subgradient, okay? I'm just using gradient as a placeholder. This dot product with x minus y should be greater than or equal to 0. Okay, so we have got three definitions here. Now, of course, you can add a contradicting term to the right hand side of each of these and talk about strong convexity as well, right? Or make these inequalities strict and call strict convexity. So those are small variants. There's of course another definition which we, or rather another property which we have invoked and proved as well, which is that the Hessian at X should be positive semi-definite. Right, that's another fourth definition. But that's the second order derivatives. Okay, so I had flashed this at the end of last class and talked about these properties. So the F is convex on D if and only if it's gradient. Now it's if and only if. The gradient being monotone and is an if and only if condition. However, subgradients wise, we can think a little bit more. So gradients are basically giving so monotonicity of gradients is giving you a definition pretty much. Where moment I say if and only if, it's a new definition, right? That's why I have taken the liberty of calling these to be definitions of convexity, depending on, of course, the existence of gradients and existence of Hessians. So this may be the most general. Therefore, it's safest to start with the kind of midpoint convexity, line segment convexity definition. Okay. So you had these three definitions. Gradient being monotone is equivalent to function being convex. Gradient being strictly monotone is equivalent to function being strictly convex. And likewise, there's a strong convexity, the gradient being strong, uniformly monotone. It's called uniform monotonicity, but basically it's that the dot product is lower bounded by a quadratic term on the right hand side involving x minus y norm square. Okay, so now a question for you guys is, what happens if you have subgradients? If a function is convex, is a subgradient guaranteed to exist? And subgradients is what entire ML today thrives on, right? So what happens? Is it if and only if, first of all? Well, by the way, what about subgradient here? If the function is convex, we knew that subgradient exists. So there was a subgradient. There are subgradients rather. A class of these vectors, right? That we know. We proved it. I mean, I've given you the hint of the sketch of the proof. So this property should be fine. Question is about this property, which is the monotonicity. So if you look at the proof sketch we had, what are the proof sketch? You have to see there are loopholes, right? So we saw the proof sketch. How did we prove necessity? If F is strong, so we started with F, strong convexity. If F is strongly convex, then we have an extension of this first order condition. All you do is add the two, one for y, one for x. You see, all of the Fy greater than or equal to Fx plus, no, whatever, right? The quadratic approximation lower bound. And Fx is greater than or equal to the quadratic approximation around y, the lower bound. For x you use y and for y you use x. Add them and then we as basically, so after adding them, then we consider this interesting thing, which is let z be x plus t times y minus x. So you're basically taking a point in the line segment joining y and x. And then you know from mean value theorem that for that t, I mean, basically there should be a t for which phi1 minus phi0 should be phi dash t. Right? So this is the proof. I'm not going to go over this. That's how the proof was, this condition was shown to be necessary. Does it fall through the cracks somewhere when it comes to subgradients? That's the only thing I wanted to look at. Does it? Yes or no? the proof, or does it stand? Anyone? So what about this mean value theorem? Will this hold if the function is not differentiable? I mean, it's not that the subgradient gives you all the properties of gradient, right? The mean value theorem not guaranteed to exist, right? So there's a problem if just extrapolating these two subgradients. You can't show that this is the necessary condition. The existence of subgradient is fine, but the monotonicity, this proof certainly is not good enough, right? Likewise, I mean, the rest I'm not going to go through. You can also show, you can also show the sufficiency, but this is the main problem, the mean value theorem. Okay, so I think with that we have covered a whole bunch of conditions. Let's now move on. Okay, let's now move on to the concept of minima, local minima, global minima, and how to minimize, right? What are the conditions for minimization? So here's a local maximum in blue. Here's a local minimum in shaded yellow, right? For this function, 3x1 square minus x1 cube minus 2x2 square plus x2 raised to 4. So this function is certainly not convex everywhere, right? At least from visuals. But what you are able to do is eyeball points of local minima, local maxima, and yes, around the point of local minimum, there's some convexity. Around the point of local maximum, there is a concavity, right? You understand what is concavity? I hope I don't have to define it. The negative of convex function versus so negative of a convex function is concave. So now how do you reach these points? Like the question, how do you show that a particular point is a point of minimum? Local, in this case, right, looks like this point might be a point of even global minimum, possibly. Okay. It's shifted a bit. Let me just reposition this. I meant here. Yeah, the rest are okay. So here are definitions of absolute minimum, maximum. So absolute minimum would at point C would mean that f of x is greater than or equal to f of c for all c, for all x in the domain. Likewise, for maximum, f of x should be less than or equal to f of c for all x and d. However, as I showed the definitions, flashed the definitions, there's a notion of a ball and basically an open set. So if there's an open set whose canonical case is a ball around a point for which the minimum is a local minimum, is a global minimum or absolute minimum, then we call it a local minimum. Okay, so the function like this. So at this point, I can draw a ball. I can draw an open set. So in this case, we have taken the degenerate case of an open ball at this point x with a radius epsilon. So if there exists such that the open ball such that for all Let's just call it C. For all x in the open ball, C comma epsilon, f of C is less than or equal to f of x, then we say that f of C is a local minimum. And C is a point of local minimum, and vice versa. Right, if I give you C and say it's a point of local minimum, f of C would be, sorry, if I say C is a point of local minimum, then f of C is the local minimum. And if I just flip these inequalities, greater than or equal to, then this becomes the point of local maximum. That's it. In general, you have the notion of a local extreme value. Okay, extreme value basically means that it's either a local minimum or maximum. This is clear. So very simple definition. Okay, so now how does it relate to the first order conditions, right? The first order conditions, do they give me some way of characterizing a point of local minimum, a point of global minimum, maximum, both global and local? So it turns out that the subgradient gives you a sufficient condition test for global minimum. So there are four things we are talking about. Okay, let's actually draw a matrix. It'll be useful to have all of these in one place. So you're talking about local global, one dimension. We're talking about necessity and sufficiency as another condition, and maximum and minimum. Okay, so three dimensions: local versus global, min versus max, and necessity versus sufficiency. So it turns out that this, innocuous thing, right? This is a very simple inequality, gives you a very interesting sufficiency condition for global minimum. Okay, so what will we do? We'll see how global min and sufficiency are brought together using subgradients. Of course, this is in the context of convexity, because subgradient otherwise is not even guaranteed to exist. Okay. Okay. Obviously, we'll see a little bit more on non-convex functions. Now, any point of local minimum for a convex function is also a point of global minimum. Okay, so that's another connection we'll see. So local min and global min, they are connected for convex functions. That's the second connection. And the third is, well, I haven't written that, so I should actually write down. There's a fourth: strict versus strong. I mean, yeah, strict, not versus, strict / strong convexity. Right. So it turns out that if the function is strictly convex, there's only one point of global min. Okay, so So this is a third correction. Global min for strictly convex function is unique. Uniqueness. Okay. So these are some interesting conditions. We'll see more. Some necessity conditions will keep emerging. But let's start with these very simple. Okay. So I'll start with the blue part first, right? So in fact, try and erase still one. Can't find the lister. Where is it? Oh, so I'm going to really erase pretty much all these definitions except for this one. Okay, so I'm going to replace this gradient with a generic subgradient, and the notation for subgradient in general will be as h subscript f, argument of x. Okay. Right. I mean, I've just added an f subscript and argument x. So my question is, how is this giving you a sufficient condition for global minimum? That's the first part, right? I'm going to do the part in blue. Sufficient condition for global min. Right? Let's say the global min is being claimed at a point x star. Any suggestions? How would I use this existence, right, of subgradient at x star and to derive a sufficient condition? Yes. Sorry. If we set it to be 0. So since Jesus is looking for sufficient condition, he's saying it could just be h f x star equals 0, right? Because this will imply, what will it imply? That f of y is greater than or equal to f of x star plus this h of x star transpose y minus x star. And this part will go to 0. Right? Which implies that f of y is greater than or equal to f of x star, which anyways was for all y in the domain. For all y in domain. Very simple. A subgradient that vanishes or a point at which the subgradient vanishes must be a point of global minimum for the function. This is clear? Okay, so just we are stating the same thing for a convex f. We would have for all y in the domain, f of y is greater than or equal to f of x plus hx y minus x. And if 0 is in the subdifferential, so this is how we should write it more formally. I mean, I've just said hf equals 0. But what we really want is there must be a 0 in the subdifferential at x. Then I can just set, it need not be that all the h's go to 0, okay? Please note this. And this again will come up in lasso, right? One subdifferential going to 0 is sufficient. Not that the only subdifferential, only element of the subdifferential should be 0. Well, if it's gradient, then the gradient must be 0 because the gradient is going to be the singleton set that subdifferential will be. But otherwise, it need not be. Okay, so this is the more formal proof. What I wrote on the board is more informal. So then, yeah, this is sufficient. 0 being the subdifferential, just set it to 0. Or rather, this inequality holds also for hx equals 0. And therefore, f of y will be greater than or equal to f of x for all y. Clear? It, yeah, just linearizing it. H equals 0 being a subgradient means that for all y, this hold. The analogy for the differentiable case is that the subdifferential is a singleton set, which is the gradient. So it holds in that simple case as well. The question is, this is fine for sufficient condition. What about necessary condition? Right. So let's say the function is differentiable. So far, we didn't assume there was differentiability, right? We didn't have to assume this differentiability. But if there's a differentiable function, possibly even non-convex. In fact, I'm adding more dimensions. Right. So I'm saying, well, strong non-convex. And in fact, I'm adding more points. Differentiable versus non-differentiable. You can consider all these conditions, all these cases. So here, just leaving a question: what if the function is differentiable, possibly non-convex, and I want to consider its local minimum? So that's invoked another combination here. More like a question, but we'll do one at a time. Okay, this is the following combination: non-differentiable, just using different color, necessary condition, both local or global, right? So that and min. Well, this will also hold for max. We'll see that later on. Okay. I'm sorry. I meant differentiable. Okay. I meant differentiable non-convex. I meant to underline this. Differentiable non-convex. Any thoughts? The most obvious guess that most of you would have: if it's differentiable, gradient should go to 0. I mean, you would probably say this even if I wake you up from sleep, right? So these are called critical points. The points where, this is, critical points of convex functions are global minima. So what we are saying here is critical points are points where the gradient vanishes. For convex functions, it turns out that they actually turn out to be global minimum, right? It gives you a moment you say that gradient is 0, it's basically a sufficient condition. That's what we have seen so far, right? So suppose f is convex and differentiable, then if gradient is 0, then x is a global minimum, right? Just by virtue of what I've shown on the board. This is a sufficient condition test, right? So this basically means that the moment you set the critical point to 0, you hit a global minimum for convex functions. That ties together things very neatly from sufficiency to necessity. But we'll look at necessity very soon. In fact, last class we derived the global minimum for fx is 1/2 y minus norm x square plus lambda norm x1. The other interesting thing is There's no saddle point for convex functions. What is a saddle point? You have seen a horse saddle? How does a horse saddle bend? Bend sidewards so that your feet can be hanging, and then the front it's going up, right? So that you don't fall off either to the front or the back, right? So the place where you sit on a horse, right, the seat, it has both a dip and a peak, right? So that's an example of a point which has gradient going to 0. It's a critical point. It's a local minimum in one direction. It's a local minimum in one direction. Local maximum. I'll show that. I'll illustrate that on the board, but it's important for you to imagine, right? So interestingly, when you have convex functions, they cannot have saddles. Okay, let's look at this. So this is a non-convex function, 3x5 minus 5x cube. If you look at the derivatives and set it to 0, the critical points are the places where the derivative vanishes, which are 0, 1, and -1. Can you check that? Okay, 0, 1, and -1. Now it turns out that -1 is a point of local maximum. You can see that it's local maximum here, and there's a local minimum at 1. The point 0 is a saddle point. Okay, it looks like it'll kind of take a dip from one direction, but you go to the other direction, it's only further increasing. From one direction, it looks like it has taken a dip, but from the other direction, it looks like it can dip further, and vice versa, like a horse saddle. I mean, this is basically a one-directional saddle. What you all visualize for a horse saddle is two-dimensional saddle. We'll show that also. Is this clear? Example clear? Right. So here f dash goes to 0, but it's a point of local maximum. Here f dash goes to 0, it's a point of local minimum. And this saddle point exists in non-convex regions, right? But a convex function can never have saddle points. Okay, so I mean, just since it's related to that, I'll just write here. So critical points So saddle point is a critical point that is neither local min nor local max. However, I must tell you that in reality, when we are trying to do solve optimization problems, saddle points are quite commonplace, right? Because we are dealing with non-convex functions, and a lot of reality is about escaping saddle points. Okay, so here's our illustration for 3x1 cube minus x1 cube minus 2x2 square plus x2 raised to 4. Now this has exactly what we referred to as Haas saddle. In fact, you can draw this for a simpler function x1 minus x2 square. You can draw it yourself. But specifically, here you can see the horse saddles are here, right? Here. Sorry, here. Here. It has a, if you go down this path, you have a local minimum. If you go this way, you have a maximum. This is an example of saddle. Now, all these saddles do not look as symmetric as horse saddles, right? They can have different rates of growth along different directions. Right? So, let's do the following. We have discussed two conditions. Basically, critical. I haven't really given the proof for necessity. Necessity, I said that saddle points are points of local minimum, but critical points are points of local min or max. We'll get to that. But let's do the following. Let's apply this to this very interesting lasso, the sufficient condition. Imagine that F is the lasso loss, right? 1/2 y minus x norm square plus lambda norm x1. Let's try bring out your notebooks. Let's try and write the sufficient condition. You'll find it very interesting. Okay, I'll erase this proof here and try and write down its condition. I'm just trying to apply sufficient condition test to this problem of lasso. Okay, my F is 1/2 y minus x norm square plus lambda x1, and its subgradient is h, which is x minus y plus lambda s. But I'll just write this specifically. Now, sufficient condition at x should be what? That it goes to 0. Right? Now, what does that imply? It implies that y is given, okay? Y is given. X is what we are trying to estimate. X minus y plus lambda is equal to 0. But remember, lambda s itself is a function of x. So better to write a subscript, right? So in fact, if you recall from the last class, what I've written on the board, Si is sine of xi if xi is not equal to 0 and is equal to -1, anything in -1 to +1 if xi is equal to 0. Right? Now, how do I solve this to get x? They are pretty much there. And I would suggest write it element wise. Okay. So if you want, write it this way, right? I'll restate the whole thing. Therefore, if. So now you might wonder, how can I characterize xi? Yeah, here we say if xi is not equal to 0, then it's sine of xi. But xi is what I want to estimate in the first place, right? How would I know the sine of xi if I don't know xi? So what do we do? The chicken egg problem. Yeah? Assume. Eventually, what would you like? Eventually, what would the condition look like? It should be in terms of yi's, right? Okay, so why don't you write? I'm just writing whatever you're saying. Okay, so if xi is greater than 0, well, greater than 0, strictly greater than 0, then si will be +1. And I'll write down this expression xi minus yi plus lambda equals 0. If xi is less than 0, si would be, the sign would be minus 1. And xi minus yi minus of lambda equals 0. If xi equals 0, si is in minus 1, 2 plus 1 closed interval. And xi minus yi, well, if it's equal to 0, I'll just remove xi altogether. I'll have, now this si can be anything between 1 and minus 1, right? By the way, si itself is not our goal. We are not interested in si. We are interested in xi. Okay, so we'll write it anyways. So how will this be? This will be minus yi. Yes, you won't need to help me. Minus yi plus lambda times something in minus 1 and plus 1 equals 0. So now you think differently. So the suggestion was to assume xi is less than 0, greater than 0, and or equal to 0. Look at what the conditions look like. So I did this, and then minus yi plus lambda times minus 1 to plus 1 interval is 0, which kind of amounts to saying that yi will be in minus lambda to plus lambda closed interval. Okay, so in case you can't see this on the board fully, I'm just writing this down here. So if hi is 0 and xi is greater than 0, that's what I've written. Then xi equals yi minus lambda. Okay, so I've gone one step further. Right. So what I want to do now is derive xi's, not yi's. Right. So I'm going one step further. I'm saying, well, if xi minus yi plus lambda is equal to 0, that means xi should have been yi minus lambda. So if xi is greater than or equal to 0 and xi is yi minus lambda, then what should hold about yi? See, look at these two conditions. Maybe I'll start using a different color here. Look at these two conditions. Xi I assumed was greater than 0, right? The keyword that he used was assumption. Fine, if xi is greater than 0, xi turns out to be yi minus lambda. So what would be the condition for yi then? Yi is greater than lambda, correct? Can I just apply this logic in the reverse direction now? I'll just say if yi is greater than lambda, then xi is yi minus lambda. I'm going to do the same thing in, why don't you complete it, right? If xi minus yi minus lambda is equal to 0, then I know that xi is yi plus lambda and given that xi was assumed to be less than 0 and xi is yi plus lambda, what should yi be? Right, yi should be less than minus lambda. And final is if xi is 0, exactly equal to 0, then yi turns out to be between minus lambda and lambda. The other way of putting it is if yi is between minus lambda to lambda, then xi should be 0. Okay, so this is what you see on the right hand side is the kind of interpretation, right? What I highlighted there summarily is what is happening. Summarily, if I'll write in the same order, if yi is greater than lambda, xi is yi minus lambda. If yi is less than minus lambda, xi is yi plus lambda. If yi is in the closed interval minus lambda and lambda, then xi equals 0. So this is a sufficient condition for minimum. So let's say I have my y. Y was, by the way, a simplification of matrix multiplication A with some weights, right? AW. Y was basically AW. I've just made it simple. So I'm saying given that I have some observations y, I want to match x to y such that the x is as simple as possible as per one norm. All I'm doing is as follows. And look at the interpretation. It's so nice, right? If yi is greater than lambda, I mean, I had to control the xi one norm using lambda. This says if yi is greater than lambda, then shrink yi by lambda and assign it to xi. Shrink it. If yi is less than minus lambda, which means it has high magnitude, but it is negative, then increase it by lambda. Make it more positive. If it's too positive, make it slightly less positive. If it's too negative, make it slightly less negative. But if it's between minus lambda and lambda, it is close enough to 0. Saying between minus lambda and lambda is saying it's close enough to 0. Then kill it, right? Okay, so if you want to get kind of interpret it on this line, what is it saying? It's saying that between minus lambda and lambda, set it to 0. On the left hand side, you push it to 0 by adding a lambda. On the right hand side, push it to 0 by subtracting lambda. This image should be good enough. Is this visible from behind? In either case, kind of you're squeezing it to 0. The only thing is lambda tells you a threshold, gives you a threshold within which you force it to 0. Outside that, you linearly squeeze it to 0. Okay, I hope this is clear. Yeah. There's no proximal here. This is not proximal. This is a lasso problem where we are trying to find a solution to linear regression. So X is like our weights W. So I want weights W for linear regression such that we are constrained by one norm, which means the one norm of W, the one norm of the weights. Remember, I had shown you this collab. You want me to pull that up again? I'd shown you this collab, right? When we talked of applications. what does let me try and see if it's there sitting on the um let me just see if I can pull it up. Yeah, here. Here, I think W nice. Oh, yeah. So this is a function, right? I was trying to fit. If I this green function, right? If I don't put any regularizer, it bends a lot, right? And then I think I had shown either this or another this ridge regression. So ridge regression tries to say, okay, instead of making it so curved, ridge regression adds this L2 norm. Ridge regression is about L2 norm, and it's regulating the curvature to some extent, right? And what does lasso do? I don't know if lasso was in the same. Yeah, lasso was in a different one. Maybe lasso was in a different. Yeah, it was in a different collab notebook. I can't find it right now, but I had shown my note. I put it on the Moodle, right? So where we had shown that if instead of L2 norm, so instead of L2 norm, if I used L1 norm, right, many of the lambdas start going to zero. You remember that? Many lambdas start going to zero. Why do they go to zero? It's because of this operation. Any y which is close enough to zero, modulo minus lambda lambda, there's just clip to zero. Is this clear? Yeah, I'll post this collab link again. Um, so that's why lasso gives you sparse solutions. It's because of this clipping, right? What was the interpretation I gave for sparsity long back? When I talked about L1 L versus L2, you remember? There was one more interpretation I gave. What does the level curves of L2 look like? Circles, right? What does the level curve of L1 look like? This is what the L1, right? This is the L1 norm. Level curve. This is L2 norm, right? So it typically happens that dust accumulates in corners of the room, right? Where does the dust accumulate in this room? The corners. Is there a reason it accumulates at the corners? For physics, there's something interesting happening that they are accumulating at corners, right? Solutions also tend to accumulate on corners here. I mean, by virtue of this sparsity. So basically, L1 norm induces sparsity, right? Uh, the sparsity is reflected in this corners, right? There will be lots of corners. We are just showing two corners, but there will be lots of corners in the sense there will be corners which have some components going to zero. There's a tendency to gravitate towards those, right? Is this clear? Okay. So we have done an example of sufficient condition. How can be practically used? This is super practical. Right? Okay, so this has a name. The solution X star is S lambda Y, right? Entire thing which I've talked about is this S lambda Y. And this is called a soft thresholding operator. You take Y, if it's greater than lambda, clip it by lambda. If it's less than minus lambda, increase it by lambda. If it's between minus lambda and plus lambda, set it to zero. This is called a soft thresholding operator. Right? In fact, you can now verify. See, this is a sufficient condition test. Take S lambda y, right? Take S lambda y and plug that here. Take X to be, verify. You have to verify as your homework. Verify that X in S lambda y is a solution. So you need to verify this. That we have a sufficient condition test has given you a solution. Now, you talk about proximal, right? Very good that you brought up proximal. If it's so simple, right? If, oh, non-differentiable convex function, suddenly subgradient is solving the problem. I'll never go hungry. The world hunger problem is solved. Optimization problems get solved. Is that the case? And a simple complication. If I add a matrix A here, y minus ax, what do you think will happen? Will it be so simple? Y minus ax norm square. I'll tell you things become complicated. Now I was dealing with the x. Instead of x, think of it as w, right? What is lasso? Lasso is y minus a w norm square plus lambda norm 1, lambda of w norm 1 is to be minimized. So if I put an a here, what will happen? Just one a. A is, you understand what I'm talking about, I hope. Right? So I am just changing this to fx and half, let me call it w. Y minus a w norm square plus 1 norm of w. Do you think solution will be so simple? Okay. So it turns out that with slight changes, the solution doesn't, you may not be able to get. I mean, I'm not saying for all values of A it will be complex. We just took simple example of identity A. But what can be done is we can still use a sufficient condition set test. We can still use lasso, but with respect to a simplified problem. Do you remember the proximal operation? I mean, I didn't talk about the proximal operation, but the subgradient with respect to proximal operation. So it turns out that you can do what we call proximal gradient descent and use lasso, so use the sufficient condition test there. We'll revisit this. So this lasso is our favorite, will keep coming up. Okay. When we add a matrix, when we introduce a matrix A, things get more complex. But this will become a subroutine. The entire thing will become one small part through proximal gradient descent. Is that clear? So since you brought up proximal, yes, there is a connection. Though we are not doing any proximal here. There's no proximal in this slide. But it will come up. Okay. So I did this, right? Subgradient based sufficient condition test for global minimum. I hope you're done. It's clear, right? Whether it's convex, it's of course going to be a condition for global minimum. If it's not convex, then subgradient itself may not exist. So the sufficiency condition we can't even talk about. Won't exist. Sorry, everywhere. So now let's look at the second, which is any point of local minimum is also a point of global minimum. A point of local minimum, what is the name we gave it? I'm sorry, a point where gradient vanishes is critical point, right? So that we have already talked about, but we'll talk about a different condition now. The one in this part. Any point of local minimum is also point of global minimum. We'll defer the discussion on critical points a little bit. I'm going to erase the right hand side. Has everyone noted this down? Here is it. Okay. So to do the second part, So this is a much simpler proof. So if x is a point of local minimum and y is some point of global minimum, what are we trying to show? What will we try to show here? Any hints or guesses? This for a convex function f, right? This is the part I had written in this brown color. Point of local min is also point of global min for convex function. So I'm claiming that, oh, if the point of local min is x and the point of global min is y, then what would happen if this is x, this is y? What do I want to prove? Any point of local minimum is also point of global minimum solution. What do I want to prove here? X equals to y. Do we need to prove that? X equals to y? We are not concerned with x being equal to y. Point of local minimum should be a point of global minimum. There could be multiple points of global minimum. All we are trying to show is that f of x should be equal to f of y. Okay. The claim is that f of x in this setting coincides with f of y, not x with y necessarily. How do you prove this? What would be your proof methodology? Very simple. Sorry? Contradict. Well, yeah, that's one way. Contradiction. You can show that if f of x is taken to be greater than f of y. Let's say claim. Suppose f of x is greater than f of y. Then what would I do? X is a point of local minimum. And we are saying, oh, it's a local minimum. It's like this, right? This is x here, this is y, f of x is greater than f of y. Obviously, you laugh at this because it's not a convex function. We are struggling to find an example. But let's say, for argument's sake, f of x was greater than f of y. Then what will I do? Sufficiency condition, why do we need here? You're saying we'll invoke sufficiency condition, but here we are not making a sufficiency condition claim here. We are saying if x is point of local minimum, f of x must equal f of y, and we are trying to contradict that. So what would I do? The intuitive thing is, can we construct a new point z and show that f of z will turn out to be less than f of y, which is a contradiction. If you tell me that local minimum is not global minimum, I'll do something between the local and the global and create a better global because the function is convex. Can you do this? Okay, I'm going to pictorially depict this. Okay, so here's it, right? X is a point of local minimum. Y is a global minimum. F of y is less than f of x. Exactly what I've written there. Now I'm going to say if x is a point of local minimum, I know that there is a ball, right, of radius epsilon. There exists a ball with radius epsilon such that for all points, you remember the definition. There's an open ball here So I just replace C with X. That's a local minimum point of local minimum. Such that for all Y, this is Y. I mean, actually Z. Let's use the word Z. Y is a fixed point for all all Z in the ball centered around X with radius epsilon. F of X is less than equal to F of Z. I'm just using the definition of local minimum. Construct the ball epsilon here, right? Epsilon radius ball. And what is it that I'm going to do? I'm trying to construct a Z, a new point Z. Where will that Z should be? Where? Well, we don't know. Okay, some Z. But it makes sense to have Z on the line segment joining X to Y. Because that's where I can talk about convexity and all that, right? I mean, the line segment joining 2 points and then say the function at some point in the line segment, right? The convexity, right? Function at that point in the line segment is less than the convex combination of the functions. That's where I can say that, well, if I look at the convex combination of fx and fy, that particular convex combination, that seems to be greater than the function value at z. That means I've got a new global minimum. Is this clear? That's the whole idea. So this is proof by contradiction. This same picture I'll keep bringing up so that I don't need to write everything everywhere. So this is what you're saying. Since X corresponds to local minimum, there exists an epsilon greater than 0 such that you can draw this ball and I will now construct a Z within the open ball. So open ball, sorry. Open ball and show that f of Z is less than f of X. Right? And f of Y is also less than f of X. F of Y is because f of Y is less than f of X already. Right? That's known. I mean, that's supposed to be our starting point. But we'll show that f of Z is less than f of X as well. And show that, well, in fact, f of Z is going to be less than f of Y. Okay, how do we do that? That's the rest. Okay, so consider this point Z, and how am I going to construct Z? Z is theta y plus 1 minus theta x. The only thing is I have to keep this theta, manipulate this theta to be some epsilon divided by 2 norm of y minus x. It's basically halfway, right? It's basically halfway between x and y, as I was showing in the figure. So let's try and do that, right? So this Z is x plus, okay, I'll just, oh, sorry, is theta y plus 1 minus theta x. Where theta is epsilon by 2 norm y minus x. Now the rest is simple. Since f of y is less than f of x, okay, f of y is less than f of x. And now apply conditions of convexity. Why don't you try writing? Simple. What do we know of convexity? F of z is less than equal to theta fx plus 1 minus theta fy. I know that f of y is less than f of x. So I can do that. I can say this is less than, I won't do that later. One at a time. So let's substitute for theta. What happens if you substitute for theta? Theta is what? 2 by norm y minus x. So try doing that, right? Please write. You're pretty much there. It's very simple. For this particular combination, what happens? Okay, in the interest of time, so I'm just going to run you through this, right? So if so, just first of all, you should evaluate that z minus x is epsilon by 2. Z is within the epsilon ball. So for this setting, this z will turn out to be, as I said, here is x, here is epsilon, here is y. No, z minus x is epsilon by 2. So basically, z is sitting somewhere here. So it's within the ball. F of z is supposed to be greater than equal to f of x. Right, and then I'm using the fact that if it's a convex function, f of z is less than equal to exactly what I wrote there. So now when I write these two together, what happens? It's simple, right? If it says f of y is less than equal to f of x, we'll have theta f of x plus 1 minus theta f of y is less than f of x. So what have I done? F of z is less than f of x. I've actually manufactured a point. Sorry, I manufactured a point. I have done slightly different, but yeah, we could have done other ways also. So to show that, yeah, f of z is less than f of x. And this is what I meant. We have manufactured a new local minimum. So I assume that x is a local minimum, and I use an epsilon ball in which x is claimed to be the local minimum, and use the convexity property of function f to manufacture a point within the ball for which the function value is less than the so-called local minimum. Right? So I manufactured a new local minimum. Okay, so that's yeah. So f of y is less than equal to f of, so f of z is less than equal to this entire thing, which is less than, strictly less than, sorry, theta times f of y plus 1 minus theta times sorry, theta times f of x plus 1 minus theta times f of x. Right, because f of y is less than f of x, which is equal to f of x. So f of z is strictly less than f of x, though z is lying within the epsilon ball. Okay, so you can't afford to have a local minimum in convex function not coincide with a global minimum. Otherwise, we'll start manufacturing new points within the epsilon ball that defines the local minimum itself. Now, it turns out that if the function is strictly convex, and this is a much even simpler thing, right? Then every point of local minimum must be a point of global minimum. Sorry, every point of global minimum is unique. So what are we saying here? If x and y are 2 points of global minimum, then they must coincide. You can't have that x is not equal to y. And that again we prove by contradiction. If x and y are not equal, then I'll show that if I consider a point x plus y by 2, it will have a function value less than f of x and f of y because of strict convexity, right? This is midpoint convexity, right? So then f of x plus y by 2 is less than half of fx plus half of f5, which is same as fx. So I manufactured a new point through midpoint convexity, a new point which is a global minimum. So if 2 points x and y are points of global minimum, they must coincide. Okay, so that's the third property we have. a global minimum for strict convexity, this one, right? Strict convexity global minimum is uniqueness of global minimum for strictly convex function. Okay, so then slightly associated question, right? Now, does global minimum always exist? Okay, so I've considered this function e raised to x. Is e raised to x convex? It's convex, right? Does it have a global minimum? Hmm? How does it look like? So if you plot it, it's bounded below by 0. As x tends to minus infinity, it tends to e raised to x tends to 0. So it goes like this. So does it have a global minimum? It doesn't have, but it is lower bounded. It turns out that there are some nice characterizations under which a function will have global minimum, a convex function. So if f is a convex function, and suppose there is one non-empty bounded sublevel set. So you remember what is bounded, closed set we talked about, but bounded set, okay, I didn't talk about bounded set, but bounded set is where the limit point, every Cauchy sequence basically, a sequence of points that come close, increasing close enough, they converge, right? So every bounded set, let's not worry about that right now, but under a fairly generic condition, there just needs to be one non-empty bounded sublevel set, L alpha. Then f has a global minimum under the simple condition. So that there aren't then too many. I mean, under fairly generic conditions, you can actually talk about global minimum. But of course, that doesn't mean that you don't have to deal with this problem of e raised to x style functions. Okay, so if f is continuous, it contains a minimum over a closed and bounded set L alpha at some x star. So this L alpha is also the x star is also global minimum. So what is this f of x star? F of x star is basically where you have this boundedness. So here I've actually shown this depicted this. So if of x star is less than or equal to alpha, then it means that for any x which is not in L alpha, f of x will be greater than alpha, which is greater than or equal to f of x star. Okay, so this just shows that this is a very useful condition. Yeah, here is the depiction, pictorial depiction. This is a set of all points L alpha such f, which is x such that f of x is less than or equal to alpha. So if this is bounded, then there must be a global minimum. Okay. So it doesn't always exist, but under this condition, it does. Any questions? So this was an aside. This was not to be delved into too much right now. The next point, which is a fairly straightforward point, I almost kind of assumed it is proved, which is that critical points. Critical points are points where the gradient vanish. So the gradient vanishing is a necessary condition for local a minimum or max, right? So if it's convex and differentiable, then the gradient must vanish at that point. Sorry. If gradient vanishes at the point, then x is a global minimum. How do you prove this? It's a very straightforward thing. What do you know about sufficiency condition for convex functions? The subgradient must vanish. Right? So if gradient goes to 0, then this is basically saying that 0 is in the subgradient, subdifferential. So this part is very simple. right? But what do you do if you want to deal with? Yeah, sorry. What if you want to look at necessary conditions? This is still talking about sufficiency. Necessary condition is that if x is a point of local minimum or global minimum for a function, the gradient must vanish. Okay, so we'll do that a little later. But for now, you can assume that this is also fairly straightforward to prove. Right? So we are done with most conditions here. Did we miss out on any condition? I mean, there are some combinations we'll visit later on. So yeah, this is the condition which is for non-differentiable convex functions. So non-differentiable, sorry, for differentiable non-convex functions. Differentiable and non-convex, the gradient f going to 0 is necessary. Yeah, but we need to qualify this a bit. I'm not proving it right now because we want to deal with constraints. Okay. This doesn't easily hold the moment you have constraints. So that's why we are holding back a bit on it. The generic convex optimization problem is that you have to minimize a convex function, but you are also given some constraints, GIs and HIs. So GIX is less than or equal to 0, HJX is equal to 0. So I'm going to leave you with a thought and then we'll continue with this next time, right? Why the necessary condition is being deferred a bit. So let's say, these are the sublevel sets of a convex function. And I put some condition. So this, let's say these are sublevel sets of the function f. Okay, fx equals c1, fx equals c2, and so on. And I have a constraint here in the form of g. And only one constraint, g1 x equals, say, c. These are c1, c2, c3, and g1 x is equals, in fact, let me take the case of is less than or equal to c. Okay. This is my constraint g. So the intuition says that if I had no constraints, right, if without g, gradient fx equal to 0 appears necessary condition. Okay, we have not proved that, but the critical point, extrapolating from, right, from the calculus of single variables, we know that f dash x goes to 0. We want to deal with this more generically with constraints. But let's assume that if we didn't have constraints, the gradient should go to 0, right? It's an intuition. What happens the moment I put this constraint? My constraint is g1x is less than or equal to 0. Okay, so if my gradient, so I'll have to start looking not only at the gradient of f, but also at the gradient of g, right? So what did we know about the gradient of f? It's basically pointing in the direction of decreasing values of the function, the 2D in the space of the variables, right? So let's assume this is f1, so c1, c2 such that c2 is less than c1. So there's a tendency to reduce it further as you go in. I can increase, I can decrease. but my constraint is G1 is less than equal to C. So what's the tendency here in G, in the G space? What happens as I go here? Yeah, it decreases. So obviously, I'm not interested in decreasing G here. That's not my intent. I'm fine if G1 X is say equal to C also, right? But the problem is in this direction, F might be increasing. So G increasing is not a problem, but F increasing is a problem, right? This is basically gradient of F, possibly in this direction. I'm just hypothesizing. So now we have a little bit of tussle. If I go outside here, I'm violating G. G X less than equal to C. If I keep going inside, I'm not minimizing F. So how do I find a necessary condition? Think about it. How do I find necessary condition that respects both the need to minimize F as well as honor G? Okay. So we'll show some illustrative figures. We'll not prove the necessary condition right away. But this is what leads you to the Lagrange conditions. So Lagrange condition for constraint optimization come from this kind of consideration for the gradient and the directions of the gradient. What do you think will happen, right? If let's say if this is a point of minimum, what do you think should be the direction of the gradient G and F? Yes, guess. You should just guess, huh? They should be parallel. Parallel in the same direction or opposite direction? Opposite direction. Which means that if I move along the gradient of G, if I move along one gradient, the other function will increase. Right? Gradient of G will increase G. Or negative of gradient of G will decrease G. But that will not favor the decrease of F. And so that's the tussle point. That's where the critical condition or the necessary condition will manifest beyond just the critical point, which is where the gradients vanish. Okay, so that's a homework problem for you to think. In fact, I had we'll continue this next time. Okay, I'll illustrate through more examples the convex optimization problem. We'll meet on Monday.